Hello gentlemen, welcome to our video on Chapter 19, Chemical Thermodynamics. In this chapter we analyze the relationship between energy and the extent of a reaction. Now, looking at energy, this comes from Chapter 14, where we talked about activation energy, and we even made reaction diagrams, which are those diagrams that, feature reactants and products to talk about if a reaction is exothermic or endothermic. So that's where we start with this chapter, and we go to the extent of the reaction, which was chapter 15, and we did some of that in chapter 16 as well when we talk about equilibrium. Now, at the heart of this chapter is this concept called spontaneity. In this chapter, the spontaneous process is a process that can proceed without any major outside intervention. So it kind of happens naturally, kind of happens on its own. We'll talk more about examples of that in a moment. Now, this is governed and anchored by the first law of thermodynamics, which says that energy is conserved. Energy in this case cannot be created or destroyed. So have to keep that in mind as we go through these processes. An example of a spontaneous process could be gas in a vessel. So if we look at this picture here from your book, we can see that we have a gas here, purple gas here on the left, and the other side is empty. If you were to turn this turnstile here, open this nozzle, you all know obviously what would happen. This gas A would go over to the part B of the evacuated chamber there. Right? That is a spontaneous process. It would happen until the gases were equal on each side. Okay, that's spontaneous. That's all we're talking about here, those kind of processes. Now, if I wanted this gas here to go back into the original flask, I could not just simply wait for that to happen. Stop doing it on purpose. The reverse direction is not spontaneous, going opposite. So processes that are spontaneous in one direction are usually not spontaneous in the reverse direction. No. An example could be like dropping an egg. If I hold an egg up at some gravitational potential energy height, it has energy there. If I let it go, it will just fall on its own, crash to the ground. That doesn't happen spontaneously the other way. Eggs don't just levitate off the ground. You'd have to give them some extra energy and get them back up to that height. And processes that are spontaneous at one temperature may not be spontaneous at another temperature. We can think about good old water here. So water, let's think, so above 0 degrees, ice melts. Spontaneously. Pretty simply. Meaning you don't have to do anything, you could just put ice in that atmosphere above 0 degrees Celsius and it will start melting. And same is true below this specific temperature. So below 0 degrees Celsius, ice freezes spontaneously. And of course, this is the reverse process of the first one I mentioned. So at one temperature, above 0 degrees Celsius, ice melts spontaneously. Below that temperature, the reverse process is spontaneous. All right, so that brings us to this concept called entropy. So 19.2 is called entropy and the second law of thermodynamics. I'm not going to talk much about the second law here right now. It's kind of a weird little law, but we'll talk mostly about entropy. So understanding spontaneity requires us to understand and examine the concept of entropy, which is given by the letter S. Entropy is a measure of the randomness or disorder of a system. So how random or disordered something is a measure of its entropy. The more random and the more disordered, the more entropic you are, so you increase in entropy. The less random and the less disordered, meaning if you're more ordered and more neat, then you are decreasing in entropy. Entropy is related to the various types of motion in the molecules, things that we've already talked about, like E. Back in the day we talked about, E equals Q plus W, that E, so internal energy. And enthalpy, H. Just like these two things, entropy is a state function, meaning it depends on the overall journey, meaning final versus initial, not the pathway in between. So all the reaction mechanisms and elementary reactions that happen in between, before and after, they don't matter. All that really matters is where you start and where you finish. So this is highlighted by 19.3, where we look at molecular interpretations of entropy. So molecules will exhibit several types of motion, and all these types of motion that I mentioned below in blue will increase entropy. So the first type is translational motion. This is the movement of the entire molecule from one place to another. That makes perfect sense. Molecules move. And then vibrational motion is the periodic motion of atoms within a molecule. So within a molecule, we know that within a molecule, the bonded atoms are vibrating in place. And lastly, rotational motion. This is the rotation of a molecule around an axis or around a bond. So let's say we have a molecule, it's going to be spinning on its own axis, kind of like the Earth does on its axis. And additionally, you could have a single atom rotating around a bond. So if we have an OH bond, that hydrogen on the end can rotate, clockwise, counterclockwise around that single bond. Okay, and entropy tends to increase with increases in temperature, volume, and the number of independently moving particles. And I'll save my example for down here. I won't go into it now. Entropy increases with the freedom of motion of molecules. This is a big one, very big one. So an example will be phase changes. So we obviously know our basic phase changes, solids, liquids, and gases. We'll stick with those. Solids are, packed tightly. They're vibrating due to the intermolecular forces holding them together. Liquids, they're spaced a little further apart, and they have a little more freedom. Gases, as we know, of course, are independent, and they are moving around with high levels of kinetic energy. So the entropy, as we go from solids to gases, entropy, S, is going to increase. So if we look at the entropy of a gas versus the entropy of a liquid versus the entropy of a solid, entropy is greater in that direction. Now, entropy decreases when the formation of new bonds decreases the freedom of motion. So in a chemical reaction, if you had two gases are more entropic, right? They have higher entropies. If they react together and somehow form a solid, so if I have gas plus gas in a chemical reaction, and they somehow form a solid, those new bonds that decrease the freedom of motion, meaning I have a solid now, that would mean overall in this reaction you have a decrease in entropy. Now my third law of thermodynamics, I know I skipped the second law, but third law says that the entropy of a pure crystalline substance at absolute zero is zero. So the entropy of a pure solid or a substance at absolute zero is zero. That means at the lowest temperature possible, 0 Kelvin, we have no entropy. This is when all molecular movement ceases. And if that doesn't make sense to you, that means stops. Sorry, I wrote ceases very raw there. And at this point, we haven't reached absolute zero. It's very difficult to get to a place where everything stops, but we've gotten pretty close to it. So we know that the concept is real and the theory is right. So at that point, entropy is zero. So gentlemen, this is the intro to chapter 19. We'll go a little deeper with this next class. Please take notes. Adios.